So let's begin lecture 10, calculus 3. So let me continue with what we were doing. We were looking at Lagrange method of finding local max and mins with constraints. So constrained max min problems. So recall that if you want to maximize, so I will just quickly remind you that if you take a function f, say let's take this to be a function on R3, but actually it's restricted to a level surface of a function g. So let me call f a function from sigma g to R, where sigma g is the surface xyz such that g of xyz is a constant. So this is a level surface. Then we want to find the max. Then if a bar in sigma g is a local max or a min for f, so I should erase this then, and then if a bar is the local, then gradient of f at a bar is proportional to gradient of g at a bar. This we proved last time, and based on this we have the method of Lagrange multipliers. So let's do a couple of problems. So let's take a function f of xy to be x plus y. Find the max or min of f restricted to the set restricted to the unit circle xy, for which x square plus y square is 1. So here we take g. You want to express the given surface as a level surface for some g. So you take g to be x square plus y square minus 1. Then you compute gradient f. So we want a bar such that gradient of f at a bar is some scalar times gradient of g at a bar. So gradient of f is going to be 1 comma 1. Gradient of g is 2x comma 2y. So you want 1 to be lambda times 2x, 1 to be lambda times 2y. So this, and along with the constraint condition x square plus y square is 1. So these two things tell you that 2 lambda x equals 2 lambda y. So 2 times lambda into bracket x minus y is 0. Therefore, there are two possibilities, either lambda is 0 or x is y. If lambda is 0, this will not work, because if lambda is 0, you will get 1 equals 0, a contradiction. So lambda cannot be 0. Therefore, x must be y. But x square plus y square is 1. That means 2x square is 1. So that tells you x must be 1 over root 2 plus or minus. So the critical points are when x is 1 over root 2, y is x, so y is 1 over root 2, and when x is minus 1 over root 2, y is also minus 1 over root 2. So these are the only two critical points. Now, even though we do not have a sufficiency condition, you can figure out which one is a max and which one is a min. So if you look at these 2 points, one is over here, 1 over root 2, 1 over root 2, and the other one is minus 1 over root 2, minus 1 over root 2. And you see that note that the level curves of G are straight lines. Level curves of F are straight lines, sorry. Straight lines. x plus y equal to c. So in other words, the function is constant on the straight lines, and this, if you look at this straight line, which is x plus y equal to 2 by root 2, because your point is x is 1 over root 2, y is 1 over root 2, and this line, this is x plus y is minus 2 over root 2. So you see that the function takes its lowest at this point. So this is a local as well as global min, and this one is a local as well as global max. And as the function, if you take different values of c, you will get various lines, and then the function will take different values along this intersection of these straight lines, the level curves of f with the circle. So this is how you figure out which one is a local min and local max. Let's do one more. So find the mins or max of, let's take f of xy to be x square minus y square constrained to satisfy x square plus y square equal to 1. So your set on which you are maximizing the function is the unit circle as before. So let us take g as before to be x square plus y square minus 1. So this level curve is going to be g equal to 0. So grad of f is going to be 2x comma minus 2y. Grad g is 2x 2y. So grad f equals lambda grad g gives 2x equals lambda 2x and 2y minus 2y equal to lambda 2y. So let's look at the first equation. 2x equals lambda 2x gives 2 and 2 cancel. So that gives you, if you bring everything on one side, x times 1 minus lambda equals 0. Therefore either x is 0 or lambda equal to 1. So if x is 0, you have x square plus y square equal to 1. This you cannot forget. So this implies y square is 1, so y is 0, y is plus minus 1. That's one possibility. So you have this 0, 1 and 0 minus 1 are the critical points. These are the points in the domain, which is the circle at which the function has gradient proportional to gradient of g. So now we want to explore the other possibility. So suppose x is not 0. Then lambda is 1, has to be 1. But then you look at the second equation, then minus 2y must be 2y, which implies y is 0. Good. But x square plus y square is 1. Therefore x is plus minus 1. Therefore you get other 2 points, 1 0 and minus 1 0 are the other 2 critical points. And now which ones are the max and which ones are the mins, that you can see by looking at the behavior of f, meaning the level curves of f. So now consider the level curves of f. F is x square minus y square, so level curves of f, these are hyperbolas. So So if I look at the level curve passing through 1, 0, it looks something like this. And the value of the function here will be x square minus y square equal to 1. Similarly, if you look at this is also part of that level curve. This level curve so when c is 1, it consists of these two pieces. This is also x square minus y square equal to 1. And the other two pieces are going to be x square minus y square equal to minus 1, x square minus y square equal to minus 1. So these are going to be, so 1 and 1 0 and minus 1 0 are local as well as global max. And the other way around, 0 1 and 0 minus 1 are local mins. Good. Now let me begin with the next topic, which is going to be double integrals. So that's the next chapter. My spelling of double isn't right. So, what is the aim? The aim is the following. You are given a region D. So rather than omega, I will call it D now. So let D be a subset of R2. Be a nice region. You don't want D with holes and things like that. So there is a meaning to the word domain. So, and let us take a function f d from D to R, and we want to introduce the concept of double integral of f of x y dA over the region D. So double integral, or the integral, which is called double integral. Word double is only because it's in 2 dimensions. So integral of f over D. So before we do that, let me revise how the concept of integral was defined. Definite integral was defined in 1 variables. So recall the definition of integral a to b fx dx when the domain is an interval, when D is the interval AB. Okay, so how do you go about defining? So this was done in Calc 1. So you have an interval AB and you have a function fx. So what you do is you start with a partition. Partition is just a bunch of points. Let's call a typical point xi plus 1, and xn is b. So a partition P of AB, the interval AB, is a sequence of points a equal to x0, that's less than x1, less than x2, dot dot dot, xi less than xi plus 1, and the final one is xn, that's b. So given a partition, what you do is you look at this partition, look at these columns, and you let's take little mi to be the minimum of the function as x varies over xi to xi plus 1, capital Mi to be the maximum of f as x varies over xi to xi plus 1, and then you form the sum, or two sums, so I'll call it sums. LPF, the lower sum, which is defined by taking little mi times xi minus xi, or xi plus 1 minus xi, I equals 0 to n minus 1. This is called the lower Riemann sum. And UPF, which is the upper Riemann sum by taking the maximum of the function and so then the theorem is that when you make the partition finer and finer, these two limits, limit of LPF and limit of UPF, exist and they are equal, and that's called the definite integral. That's the way it was defined. But before that, I will make the notion of partition becoming finer more precise. One defines norm of P called, this has nothing to do with norm of a vector, it's a norm of a partition. Norm of P is defined as the maximum of the width xi plus 1 minus xi, I runs from 0 to n minus 1. So it's the largest width of this largest subinterval. So when norm P tends to 0, that means the partition is becoming finer and finer. There are many points in the partition. The points in the partition keep on increasing and the width of the subintervals decrease. So then there is a theorem. This is due to Riemann. So let f be continuous. So that's the only assumption that you need. Then limit of LPF as the length of P tends to 0 and limit of UPF as the length of P tends to 0, or the norm of P tends to 0, exists and are equal. And then the definition, this common limit is denoted by integral a to b fx dx, and it represents the area under the curve. So it gives the area, I will use this phrase, area under the curve. That means the area under the function y equal to fx, the graph of this function, on the top, x-axis on the bottom, and the vertical lines x equal to a and x equal to b on the side. So that's called the area under the curve. So now I want to mimic this definition in 2 dimensions. So now we see the analogous definition in 2 dimensions. So the idea is, I will draw 2 pictures. One is when you are looking from above. This is my x-axis and y-axis. This is your D. Let's suppose that your D is lying between A and B, and the projection of D on the x-axis is lying between A and B. Projection of D on the y-axis is lying between C and D. And let's take a partition by picking points in the x-axis and points in the on the y-axis. So I call these points A equal to x naught, B equal to xn. In between I will get xi plus 1. Similarly, y naught is C, yj and yj plus 1. And so I will get, the pieces of partition are no longer just subintervals, but they are going to be little rectangles. This I will call Rij. Rij is a set of points xy where my x lies between xi and xi plus 1 and y lies between yj and yj plus 1. So this is a partition of a 2-dimensional region. So consider a partition. So what happens if there's some part is missing? Then you don't count that. Then you only take part of D which lies in this rectangle. So I will consider a partition P which is given by, so the partition is basically given by a sequence of points in the X. On the X-axis I write cross because this is in terms of ordered pairs, and C equals y0 less than ym, which is D. And given a partition, you take, as I indicated about, let Rij be the interval xi to xi plus 1. Cross meaning you take pairs, ordered pairs. First component of the pair comes from xi minus xi, xi comma xi plus 1. Second pair component comes from yj to yj plus 1. And then you pick mi to be the minimum of the function f of xy, where xy is in Rij. Capital Mi is the maximum of f of xy, where xy varies in Rij. And then I form these sums LPF, which is sum of, exactly like what we did, I varies between 1 to n, j varies between 1 to m. I take little mij, this should be mij and this is capital Mij, multiplied by the area of Rij. And similarly the UPF will be summation 1 less than equal to I less than m, 1 less than j less than n, capital Mij, area of Rij. So if you look at what's happening in 3D, so here is my domain D, and I'm taking a partition. So that's my Rij, and I have a function on the top. So it's like a surface over this, and so you are multiplying it by, so what you are counting is the volume of this solid with the cap on the top. So this is the lower sum will give you pick the lowest value of the function in this region Rij multiplied by the area that gives you the volume of the solid. So when you take the limit, so the analog of the theorem is that suppose f is continuous, then limit of LPF as the norm of LP. So norm of LP here you can define as the maximum of the area Rij, as I and j vary over 1 to n and 1 to m respectively. So this limit exists. Limit UPF as length of as norm of P tends to 0 exists and are equal. So the definition, this common limit is called the double integral of f over region D, and is denoted by two integral signs, put a d underneath, and then f of xy dA. A stands for, because you are measuring now the area of each little rectangle in the one dimension you are measuring the length xi plus 1 minus xi. Now the question is, this definition, even in case of one variable, the definition, the way we defined it in the integral a to b for one variable, that doesn't give you actually a way of computing. So these definitions, so this is a remark, these definitions, whether f is a function from ab to r, or f is a function from D, which is a subset of R2 to R, do not give us a way to compute, do not give us a way to actually compute the value of the integral. So in one variable, how was it done? In one variable, we use Riemann's fundamental theorem of integral calc. So in one variable situation, in one variable calc, we used the fundamental theorem of integral calculus. Fundamental theorem of integral calculus, which you will prove in advanced calc. So what does it say? It says that integral a to b fx dx, this is a theorem of Riemann again, it's actually gb minus ga, where g is the antiderivative of f. That means g prime is fx. That's how we evaluated the definite integrals. So this is the statement of the fundamental theorem of integral calc. So that's why finding the antiderivatives, which is the chore that you went through in Calc 1 and Calc 2 about how to find the antiderivatives, becomes very important, because that helps you calculate the definite integrals. In 2 dimensions, we have the following analog of this. In 2 dimension, we have the following analog, in the sense that this gives you a way of evaluating what I'm going to describe. So we have the following result, and that is evaluating a double integral as a repeated integral. So this is a theorem. So again, I'm taking a function d, which is from R2, domain d from R2 to R. And now if the domain is nice, in a sense, it looks like the region trapped in between two curves, y equal to phi1x and y equal to phi2x, and my x varies between a and b. So I'm supposing my domain is of the form all xy's such that x is between a and b and y is between some two functions of x. So where I'm assuming that where phi1, phi2 are continuous, and let's assume f is also continuous. So your domain D is like this. Then in this situation, the double integral of f x y dA actually can be written as repeated integral. What you do is you fix your x and you integrate along this vertical line. So I take the function f of xy, I think of this as a function of y. I integrate it from phi1x to phi2x. So what I get is a function of x. That will be the integral on this vertical line. And then I integrate that with respect to x as a function of x from a to b. So this is evaluating a double integral as a repeated integral. So I should give a title to this theorem: double integral as repeated integrals. So the proof of this I'm not going to give, but you can see how it is going to be. Fixing a x, you are integrating on the vertical line, and then you move this vertical line to cover this entire region D. That's how. So it is conceivable that why these two things should be equal. That's not a proof, but gives you some feeling about why it should be true. As you move your x, you will be integrating over all vertical lines, and all these vertical lines fill the whole region D. So when D is of this form, then you can calculate the double integral. So now let's use this formula first to compute the double integral. So let's do some problems. Problem 1, evaluate double integral x square minus y dA over the region D, where D is the set of all points xy, where x is between -1 and 1, and y is between mod y is less than or equal to x square. Another way of saying this is x is between -1 and 1, and mod y is less than x square. What will that mean? That means y has to lie between minus x square and x square. So always first step is drawing a picture of D. Draw a picture of D. That will help you immensely in deciding the limits of integration when you write it as a repeated integral. So if you look at this, what are the bounding curves? Y equal to x square is a parabola. The other curve is also a parabola, y equal to minus x square. And what you are looking for is the region y less than or equal to x square is the region below this parabola. And the other region is the region above this parabola. So this is the region that we want. And your x is going between -1 and 1. So this is the picture of D. My picture is not so nice, but still. So I have a parabola here. I have another parabola here. And I take these two vertical lines. So that's going to be my D. So you see that D is like the one that we saw above. It is bounded above by this curve y equal to x square, bounded below by the curve y equal to minus x square, and on the sides by the vertical lines x equal to -1, y equal to, x equal to -1, x equal to 1. So therefore, by the theorem, integral, and your function f of xy is x square minus y. So this is going to be x square minus y dA this will be written as integral. First I integrate with respect to y, and this will go from phi1x to phi2x. The first curve is y equal to minus x square, second curve is y equal to x square. X will run between -1 to 1. So I integrate this with respect to x later. So I write the double integral as a repeated integral, first integrating with respect to y, then with respect to x. So this is going to be integral of x square. Now this is integration with respect to y, so x is a constant. So this is x square y minus y square by 2 between minus x square to x square. So this is going to be x to the 4 minus x to the 4 by 2 minus, when y is minus x square, we get minus x to the 4 minus x to the 4 by 2. So if you calculate this term and this term cancel, and you will get integral 2 times x to the 4 dx, which is 2 by 5x to the 5 from -1 to 1, which is 2 by 5 times 1 minus -1, so it's 4 by 5. By the way, one thing I forgot to mention, which I should have mentioned at the end of this discussion on double integrals, that the double integral is actually going to measure the volume. So maybe I'll write that as a remark here. Remark: double integral over d of f of xy dA equals the volume, just like in one variable the integral a to b fx dx will be the area of the region below the graph of f above the x-axis. Similarly, this will be the volume of a solid bounded above by the surface z equal to f of xy, below by the xy plane, and of course the sides will be cylindrical sides based on the, so if this is your d and this is the shape of the surface, this is your z equal to f of xy, then you are going to measure the volume of this solid. Volume of this solid is actually the double integral of f of xy. That's the geometric interpretation of this. Let's do another one. So problem 2. Find the double integral of something like, let's take x cube y dA, where d is given by the region is described by x comma y, for which x is varying between 0 to 1 and y is varying between 0 to x. So as I said before, the first thing is a picture of d. So y equal to x is this line, and I want things which are less than x. So you can take a point, for example, if this is 0.10, your y is less than x. So the region below the line is y less than x. Is the region below the line y equal to x. And you want y positive, so you don't want to go to the negative things. And your x is between 0 to 1. So you see that this is the triangle that you are going to get. This is your d. So the first step is drawing a picture as before. So we drew the picture of d. Now this tells you that this region looks like the one that you want. So d is bounded above by y equal to x and below by y equal to 0, and on the sides an x is between 0 to 1. So therefore this integral by the theorem x cube y d, so your function f of xy is x cube y dA will be, first I integrate with respect to y, so I take an arbitrary x and my y will run between 0 to x cube y dy, and then my x will run from 0 to 1, and that's going to give you integral of x cube y with respect to y. X cube is a constant, integral of y is y squared by 2 between 0 to x, and then you integrate with respect to x. So this will be 0 to 1, 1/2. X cube I take out. When y is x square, it is y is x, y square is x square, and y is, when y is 0, this becomes 0. So this is going to be integral 0 to 1 x to the 5 by 2 dx, which is going to be x to the 6 by 12 between 0 to 1. So the answer is 1/12. Good. If I made a mistake, how can the answer be 1? It's the area of the triangle is half base times the height. This point is 1, 1. So where is my integral? X to the 5 is x to the 6 by 6, isn't it? Yeah, no, that's right. This is not the area. You are integrating the function x cube y. So this is right. Let's do another one. So let's calculate double integral of x square dA, where d is given by set of all points x, y such that 0 is less than equal to y less than equal to 1 and 0 is less than equal to x less than equal to y squared. So you first draw the picture. So first sketch the picture of D. So I want to take, so look at the bounding curve, y equal to x square. No, x equal to y square. This is a horizontal parabola, meaning the one which opens on the side. And I'm looking for the region where x is less than y square. So if I take this point, 1, 0, this point is not in it. So it's going to be the region outside on the left side. And then you want your y between 0 and 1. So it's this region we are looking at. So once you have this, then you can just write down D is bounded above by y equal to 1 and below by the curve y equal to root x. Right? This is y equal to root x and this is y equal to 1. And x is going to vary between 0 and, so up to this point. So now you have to find out the common part between y equal to 1 and y equal to 1 square. So when y equal to 1 equal to y square, which means y is 1. So x will be then y square, which is 1. So this point is 1, 0. So x will be vary between 0 to 1. So therefore the double integral over D is going to be, I write first freeze x, integrate from there to there, which is the lower limit is root x, upper limit is 1. You are integrating x square with respect to y first, then with respect to x, x will run between 0 to 1. So this will be integral 0 to 1. Integral of x square with respect to y is x square y between root x to 1, which is going to be x square into parenthesis 1 minus root x dx, which is integral 0 to 1 x square minus x to the 5 halves dx, which is x cubed by 3 minus x to the 7 by 2 over 7 by 2 between 0 to 1. So this is going to be 1/3 minus 2 by 7, which is 7 minus 6 by 21, which is 1 over 21. Good. So now let me go a little bit further. So now we will consider regions of type 2. I call the first one of type 1. So now we are looking at regions which look like this, which are going to be sandwiched between the curve x equal to psi 1 y and x equal to, maybe I'll call this psi 2. Psi 1 y is at the lower. So you view this from the y-axis. So this is the, and this runs, y runs from C to D. So when D is of the form D equal to all points xy, where my x belongs to, so my y varies. So here I'm fixing my y and my x will vary between psi 1 of, let me write this, psi 1 of y less than equal to x less than equal to psi 2 of y, and my y vary between C and D. So then the theorem says that the double integral, if you view it this way, if the region is of this form, then you can write this as a repeated integral. But now I am integrating with respect to y first was the case we did before. Here I am freezing my y, so I will integrate with respect to x first. So I take f of xy dx and I will run from psi 1y to psi 2y. Then I get a function which depends only on y. I integrate with respect to y from C to D. So you see the order of integration is changed for this area. So note that for D's of this kind, the order of integration gets changed. That is, we integrate here, we integrate with respect to x first and then y. So let me give you an example of such a thing. So depending on the problem, when you look at the region, you can see whether it is advantageous to view this as region of the first type or of the second type. I call it first kind and second kind. So let's do another one, problem 4. Let's evaluate double integral xy minus y cube dA over the region D, where D is as shown. So I will draw rather than writing it in terms of inequalities. Let's take D to be something like this. This is the line y equal to x. This is the point minus 1, 0, and this is the line, this is 0, 1. So this is your D. So now you see that if you think of this D as region of type 1, then you will see the upper curve is y equal to 1. But the lower curve is different. It's x equal to, is y equal to 0 for the region between minus 1 to 0, when x varies between minus 1 to 0. And the lower curve is y equal to x. So there are two lower curves. So it is better to view this D, view D as a region of type 2. So then you can view it from the left side. So then the upper curve bounding D is x equal to y, and the lower curve, so that's this one, x equal to y, and the lower curve is going to be x equal to minus 1. That's this line. And y will vary between 0 to 1. So then your integral will be xy minus y cube dA, and that will be, now my integration is with respect to x first, then y, and my x will vary between the lower curve is -1 to the upper curve is y, and then with respect to y will run between 0 to 1. So then this is going to be integral 0 to 1. I integrate with respect to x, so I get x squared y by 2 minus xy cube between -1 to y, and then I integrate with respect to y. So this is going to be integral 0 to 1. I get, if I put y in the place of x, I am going to get y cubed by 2 minus y to the 4 minus, when I put y equal to -1, I get x squared by 2 minus sign, and y is -1, so I get plus x times 1 cube. -1 cube is -1, so you get plus x dy. Sorry, I made a mistake, perhaps, yes. I'm taking this term, evaluating it at y, and then I'm taking these terms and evaluating it at -1. That's my x is -1, so this will be y. Right, when I put x equal to y, and then I put x equal to -1, so this becomes y cube. X is -1. Okay, so this will be, so now if you look at this, what's going to happen is, I made a mistake again, I guess. This will be y cube, isn't it? Because when x is -1, I get plus y cube. Let me clear this again. Let me do this again. So I'm putting my x equal to y, so I get y cubed by 2 minus y to the 4 minus, I want to now evaluate this when x is -1. So when x is -1, I get y by 2, -1 square y by 2 minus becomes plus y cube. So this becomes then, if you calculate, this becomes 0 to 1. Y cube by 2 minus y cube is minus y cube by 2 minus y to the 4 minus y by 2, and so this is going to be minus y to the 4 by 8 minus y to the 5 by 5 minus y squared by 4 between 0 to 1. So this is going to be minus 1 by 8 minus 1 by 5 minus 1 by 4. The value at 0 will be minus 0, 0, 0. So this is going to be minus, and the sum of these you can find out. I think the common denominator is 40. Minus sign I have taken out, so it's 5 plus 8 plus 10, 23 by 40. Minus sign. Good. All right, so now let me do one problem where, as we saw, you can think of some regions, you can think in both ways, of as type 1 and as type 2, and then you can use this to change the order of integration. So let me do one problem like that, changing the order of integration. So let me illustrate that with an example. Let's find a suitable problem. Yeah, let's do it this way. So problem number 5, change the order of integration. So now you have a function of two variables and you are given an integral as a repeated integral 0 to 1. Y runs from x runs from y to 1, e to the x squared dx first and then dy. So I want to rewrite this. So write the repeated integral by changing the order. That's what I want to do. So write this. This is called a repeated integral when you are integrating a function of two variables, which is e to the x square here. This is repeated, write this repeated integral by reversing the order of integration. So let's do that. So first picture D. This is very important. You write this as a double integral and picture D. That is, think of the above as a double integral. Think of the above repeated integral as a double integral. So I want to write down what our D is. So D in the above problem. So first you have to picture D. So you have to write down what the D was. D is going to be all points x, y, where my x now runs between y and 1 and y varies between 0 and 1. So once you write down this description of D, then you see the line y equal to x is the angle bisector. The region y less than x is region above, isn't it? You can just take a point here, and this is point 0, 1. This is not the region above, probably it's the region, x has to be bigger, so it's the region below. And so let's see what the integral was. It's going from y to x, y to 1. Yeah, that's right. So it's the region below. And so this is the region you are looking at. Yeah, y less than x. So x goes between y to 1. And then you move your y between 0 and 1. So you see that the above integral is viewed. So when you view this double integral, let me write it this way. So the integral which was given is integral 0 to 1, y to 1, isn't it? Y to 1, e to the x squared dx dy. This is equal to the double integral on D of the function e to the x squared dA when viewed as type 2. When D is viewed as type 2 region. Now you want to view this as a type 1 region. So as a type 1 region, you will fix your x and integrate with respect to y first. So the function remains the same. If I integrate with respect to y first, y will go from 0 to the top, which is, the lower bounding curve is y equal to 0. The top bounding curve is y equal to x. And then you integrate with respect to x, x goes from 0 to 1. So this is the double integral when viewed as region of type 1. When D is viewed as a type 1 region. Let me do one more, and then we will end. So this is going to be problem 6 or 7 or whatever, problem 6. Isn't it 6? Yeah, I did 5 and then now it's 6. So again, let's change the order of integration. Let me pick something from the list of problems that I gave right in the beginning. So interchange or reverse, whatever the order of integration. So let's write this as integral 0 to 2 integral 0 to 4 minus y square y dx dy. So the moment you see that x is being, you are integrating with respect to x first, that means this is a region, the underlying region is going to be viewed as type 2. So here the underlying region D, on which you are writing this as a double integral, is viewed as type 2 region. Why? Because the integration with respect to x is first. Because integration with respect to x is done first. So first draw a picture of the region D. So D is going to be all xy's such that your x is lying between 0 to 4 minus y square and y is lying between 0 to 2. So you have to draw the curve x equal to, so what is the curve x equal to 4 minus y square? This is of the form, you see, x equal to minus y square is a parabola which opens sideways. X equal to y square opens like this. X equal to minus y square is like this, right? This is x equal to y square. This is x equal to minus y square. But now it is 4 minus y square. So you are pulling this to the right. So when y is 0, x is 4. So the picture of this, so you should be able to plot these curves. So the picture is going to be a parabola like that. So let me erase and draw a better picture. So this is our curve. This point is 4, and so you can see that this curve is going to be, when y is 0, x is plus minus 2. This is 0, 2, this is 0, minus 2. So this is the curve x equal to 4 minus y square. And now your y is going between 0 to 2. So y is going between 0 to 2. So you are looking at this region. This is your D. And you are viewing it from the y-axis point of view. That's why you write this as an integral. So you are fixing your y first and integrating from 0 to 4 minus y square. And then you vary y from 0 to 2. So how will you write? So the question is, how do you write this when you view this? Now view this D as region of type 1. Type 1 region. So then I will write this. So the lower curve. So first of all, the given expression, which was, what was the given expression? 0 to 2. And then 0 to 4 minus y square. Whatever the function may be, that doesn't change. Dx dy. This becomes integral on d of y dA, where d is as above. And so now you write it as a region of type 1. So you will first integrate with respect to y, then with respect to x. And y will run between, for a fixed x, between 0 to, so now you want to write y as this function, x equal to 4 minus y square. You can rewrite this as y square equal to 4 minus x square root. You are taking the positive root. So this will go from 0 to 4 minus x, and then your x will run between 0 to 4. So this is the same double integral when D is viewed as a type 1 region. I think I will stop here and we'll continue next time. So you need practice on this, so that should be good enough. So thank you, and so till next